So today is November 12th, and we're going to continue with chapter 11. Does anyone have any questions for me? Okay, so let's see. In the last class, we talked about constructing a confidence interval for estimating a population mean when the population standard deviation was unknown. So today's class, we're going to talk about proportion. Now, remember, confidence interval is a range of numbers, right? It tells us that the unknown parameter of that population is somewhere in that range. It's somewhere in that interval. And the beauty of this is that you can state your level of confidence. And so far, we were only using that one particular parameter, which is the mean. And we use the normal distribution. And then in the last class, I showed you how to read the t-distribution, which is based on the normal distribution. Now I'm going to ask you to recall even further back when I said that the normal distribution is based on quantitative data. So remember, data can be qualitative or quantitative. And if it's quantitative, then it can be discrete or continuous. And I said that the normal distribution is only based on continuous quantitative data. So that's how we could calculate mean, standard deviation, and all that. But in today's class, I'm going to say that we're not always dealing with quantitative data. Sometimes we deal with categorical or qualitative data. Can someone give me an example of what qualitative data is, or what categorical data is? So this is bringing you way back to the beginning of the semester. So give me an example of qualitative data. So Shubham, you say neighborhoods. Okay, so let's say zip codes or the name of the neighborhoods. I agree. Armilla, you say ages. So not exactly ages, but like age groups. I would go with that. Rad, you're saying data that is not numbers. Okay, I think you got it. So yeah, different categories like male, female, genres. Priscilla says yes, like ages in different genres. So you're all right. So a lot of experiments deals with that, right? We want to know the percentage of females who think a certain way. We want to know the percentage of brands that have a certain characteristic, for example. So sometimes we're dealing with categories. They're qualitative data. You can't use them in calculating mean or standard deviation because they're nominal. It's a nominal method. So how can we go about this? We still want to estimate something. Well, let's think about this. If it is categorical data and I want to know, let me start with a blank screen actually. So I'm going to type here. Suppose my example is I want to know about newspapers with duplicate pages. So I want to know about this particular thing. Oh wait, I should actually correct it and say newspapers. So newspapers with duplicate pages. So now that's, and I have a factory that prints newspapers, and I want to know about those newspapers that have accidentally been printed with duplicate pages. There are the newspapers that are fine, So these are different categories, right? I have category that is fine and category that has a blemish, that has duplicate pages. So now categories. I can extend this to the idea of counting numbers, discrete data. So I'm switching now from qualitative data to quantitative data. So my quantitative data is saying, okay, let's count the number of newspapers with duplicate pages. So now I'm dealing a little bit with quantitative data because it's not just a category. Okay, so I have, and I'm going to write down, let's say, for example, it's that entire factory of newspapers, and I randomly select 200 newspapers. So my sample size is 200. And then from those 200 newspapers, out of the 200, I find, and I'm making it up, 35 newspapers have duplicate pages. So now 35 out of 200 is going to tell me that this is my sample proportion. That's my sample proportion, which is denoted by lowercase letter p subscript s. And I'm also going to write it as lowercase letter p hat, because your homework and your textbook denotes sample proportion as p hat, which is the same thing as ps. So now I'm saying, let's take our categorical data, convert it into discrete data, because now we're dealing with the counting numbers, counting the number of duplicate newspapers with duplicate pages. And then I've come up with my sample proportion. Now this sample proportion is a single value. It's the result of my sample. It's my sample statistic. In other words, it's a single value, so it's a point estimate. Point estimate. In the last class, when we were talking about mean, I said X bar is my sample mean, and that was my point estimate. Now I'm saying PS is my point estimate. Okay, so from here, how am I going to get to the confidence interval? Okay, so still I'm dealing with discrete data. Now, confidence intervals require you to use the normal distribution, require you to use the Z tables or the T table, which is based on normal distribution. So in other words, you need to have continuous data in order to use the normal distribution. So I can't go from here to the confidence interval construction formula when I am dealing with discrete data, counting numbers. But there is something in mathematics that allows me to do that. And that is the central limit theorem. Does anyone remember what the central limit theorem is? What does it state? Red? Yep.
So I think that's something like the more sample size that you have, the more it'll be closer to a normal distribution.
Great. Perfect. Yes. So I'm going to switch here to this slide. Actually, I kind of jumped. Before I get to that, before I get to the normal distribution, I kind of jumped ahead. Let me read this slide and go back to what Rad said, because he was right. So far, we estimated population parameter using quantitative data. So we calculated the mean based on quantitative data. Now we're extending this concept to qualitative data. For example, male, female, brand 1, brand 2, brand 3. So we're dealing with categories. But since this is not quantitative data, we can estimate the proportion of items in a population that have a certain characteristic. So the example I just gave you, and I accidentally erased it before I could finish it. My example, I'm going to just type it out here, was about newspapers with duplicate pages. Okay, so that's a particular characteristic of interest. I'm only interested in those newspapers that have duplicate pages. So that means I can use the word proportion, the percentage of newspapers that have duplicate pages. So now we're estimating population proportion. Proportion means percentage. So whenever you see the word proportion, we're talking about percent. The percentage of newspapers with that particular characteristic. Okay, so that's what my example was about, how we switched from uh, qualitative data into counting numbers, so discrete data, and now we're switching to this percentage. We can use the discrete data by saying we're estimating the percentage of newspapers with duplicate pages. Okay, it still didn't bring us to the idea of constructing confidence interval, but going back to what Rad said, the goal is to estimate using confidence intervals. So that means we need to use the Z table or the T table, but neither Z or T use qualitative data. So if we're interested in number of items that have certain characteristic, then the quantitative data, that discrete counting number, they use binomial distribution, which is not the normal distribution. So remember, with discrete data, we can only use the binomial distribution. So this next sentence is what we need to remember. A non-normal distribution, so in our case, it's a binomial distribution, can be approximated into the normal distribution when the sample size is sufficiently large, when n is greater than 30 according to the central limit theorem. So this is why we can use the normal distribution or read the Z table or the T table. As long as n is greater than 30, we can use any non-normal distribution and approximate it into the normal distribution. Questions? So even if you deal with categories, even if you're dealing with counting numbers, discrete data, which actually tells you to use the binomial distribution, you can still construct confidence intervals as long as n is greater than 30 and you focus on a specific characteristic of interest, meaning the percentage of that characteristic of interest. So you're estimating proportion. So that brings us to this next slide. And I want to go to this slide first because this is what I was writing. I began writing on the previous blank slide. So PS is your sample proportion, which is also written as P hat. So P hat is what is denoted in your homework. Now I'm going to draw, let's say this is your population. And in your population, you have many different items. The items that have that particular characteristic of interest, so in our case, it was about newspapers, right? So the newspapers that had duplicate pages, they're going to be considered a success. The newspapers that don't have duplicate pages are considered failures. So you have successes and failures. What you're interested in is a success, which is the newspaper with duplicate pages. This is similar to binomial distribution, where we talked about success and failure. Okay, so in your population, you're going to have successes and you're going to have failures. So your idea is to estimate the percentage of successes in your population. Basically, that's your entire goal with confidence interval for population proportion. You want to estimate the percentage of successes in your population. So success could be anything depending on your experiment, on your example. So the method is we randomly select a sample. Okay, we randomly select our sample, and then from the sample, we do some statistical calculation and come up with a sample result. That sample result in this case is the sample proportion. So sample proportion is PS. And how do we get PS? That is X over N. And X is your number of successes. So in this visual that I drew here, I have 2 successes out of 3 items in my sample, out of 3 observations. So my sample proportion is 2 out of 3. So I'm going to use this value as a single point estimate to construct my confidence interval. Okay. There is another condition. Actually, that's it, I think. Let's keep it at that. Okay, any questions for me? Okay, so let's start with constructing a confidence interval for population proportion. Before we start with the formula, we have to discuss the assumptions. So there are 2 assumptions. Number 1, n times PS must be greater than or equal to 5. And also n times 1 minus PS, now this is PS subscript, not S times, so you can fix that. So n times 1 minus PS must also be greater than or equal to 5. Then only can you continue with the population proportion confidence interval formula. If not, then you have to go back to your sample, make sure that your sample size is larger in order to satisfy these 2 conditions. And you have to make sure that in your sample proportion gives you a value that also satisfies these 2 conditions. Okay, so you have to remember these 2 assumptions. Okay, so now the confidence interval for a population proportion. You can see here that this is your point estimate, your single value. So it's all based on the sample proportion, plus or minus z at alpha divided by 2. So this z is your critical value. So that means when you're dealing with proportion, you will only use the z table. Okay, you will always use the z standardized normal distribution table when you're talking about proportion, when you're analyzing proportion, times this entire thing in the square root. So I'm going to mark here that the square root value is your standard error of sampling distribution. That's not very clear, but it's standard error of sampling distribution. That's everything including the square root. So you might have seen this before from chapter 10 when we briefly discussed sampling distribution for proportion. Okay, that's the same thing where that came from. And then from this entire right side of the formula, that is your margin of error. So I'm breaking this down into 3 different parts because your homework exercises may ask you to first calculate standard error of sampling distribution for proportion, then the margin of error, which is the right side of the formula, and then your confidence interval, lower limit and upper limit. So when we start the next example, I'm going to show it to you in two different ways. First, using the table, and second, using Excel. Okay, so this is a new word problem that we're going to start. So reading, the question says, a QC chairperson, Queen's College chairperson, is interested in determining the proportion of students that receive some sort of financial aid. The chairperson randomly selects 200 students and finds that 118 of them are receiving financial aid. Use a 95% confidence interval to estimate the true proportion of students who receive financial aid. So a lot going on here. First, how do you know that you have to use confidence interval for proportion and not mean? Okay, Priscilla, because it's qualitative data, I'll come back to you on that. Anyone else? Why do we use confidence interval for proportion here and not mean? So yeah, all three of you are right, but it's actually exactly what Rad is saying. The question is asking for proportion. There's nothing saying mean. There's nothing here saying average or sample mean or mean. It just explicitly says proportion. So that's really all I was looking for. You answered above and beyond what I asked, all of you, which is fine. It's not wrong. So the question is asking me to find confidence interval for proportion. Okay, so that's the first thing. Now I'm going to go back to what Priscilla said. What is my characteristic of interest? What is my characteristic of interest? Karina, Angel, Priscilla, you're right. Students receiving financial aid. Students who receive some sort of financial aid. I'm only interested in those students. So if I look at my qualitative data or my categories, it's students who do not receive financial aid and students who receive some sort of financial aid. Okay, so I have my categories. Now the next step is, if I'm thinking about this, I'm switching to counting the number of students. So that means discrete data. So Dong Yang, you're saying that the number of successors, thinking of my binomial distribution, number of successors is out of the 200 students that the chair selected, 118 of them are receiving financial aid. So I'm just thinking out loud all the information that the question is giving me. Okay, and now the question is saying, well, don't tell us about the 200 students, tell us what the proportion is for the entire Queen's College. What's the percentage of students who receive financial aid across Queen's College, not just for the 200 students? So that's what we have to find. We have to come up with an estimate that this percentage is what this is what the percentage is. And we have to be 95% of our answer. Okay, so I'm going to the next slide. So now, writing down all the information from the question. The question says that we have 200 students. We know that 118 of them receive financial aid, and we have to be 95% confident. Okay, my formula here at the bottom is what I'm going to use. So the first thing is my PS. I know n is here, so I have to solve for ps or p hat. Okay, so looking at this here, ps is x divided by n. X is 118 over 200, so that's 59% or 0.59. So this is telling me that from my sample, 59% of students in my sample receive some sort of financial aid. Okay, so it doesn't mean that the entire population, I can say 59% because that's just a single value, 1 point estimate. I have to come up with an interval, a range, and say, well, it actually falls somewhere in this range. Now, before I start calculating things, I need to check my two assumptions. So, can I have Brandon and Hiba? Can you check the two assumptions? So, Brandon, you're checking to see if n times ps, is it greater than or equal to 5? And Hiba, you're going to tell me if n times 1 minus ps, is that greater than or equal to 5? Okay, anyone else? Rad, you said both will be greater than or equal to 5 because n is equal to 200. Yes, Dong Yan, you said yes, both greater than or equal to 5. Great, so that means we can continue. We've checked these two assumptions and we're okay, we can continue. Okay, so I have n, I have p hat, I do not have my critical value. So I'm told that I have to be 95% confident. So what I'm going to do now is I'm going to draw my graph so you can visually see how to get the critical value. Okay, so remember that with confidence intervals, we shade the center. So this is my lower limit, upper limit, and we always shade the center when you're dealing with confidence intervals. Okay, then we have the two critical values, the positive z. So I'll write positive z here, and then we have the negative z here. And we're told that we have to be 95% confident of our answer. So this area that I shaded is 0.95. My goal here is to find the critical value. Now, if you look up the table or if you use Excel, either way, you need to draw this graph so you visually understand what it is you're looking for. So if I'm looking at the table and I want to look up my negative z value, you can do either one. You can choose to do negative z or you could choose to do positive z. But we have to remember that we need to find the area from negative infinity up to, let's say, negative z. If I'm interested in negative z, I need to know that area. So that area is my unshaded area, which is alpha. So together it would be alpha, but individually it's alpha divided by 2 and alpha divided by 2. Now, how do I get that area? What is alpha divided by 2? Can someone tell me? Okay, Dongyan, how did you get that? Yep, you're all right. So you take 1 minus the shaded region, which is 0.95, and then divide it by 2. So this answer is 0.025. Okay. So I'm looking up in the normal distribution tables on the first page because I'm interested in the negative z value. I'm looking for 0.025, and I find that 0.025 at a point at the corresponding z value of negative 1.96. So when this area is 0.025, this area is 0.025. So I'm looking that up in the middle of the negative z table. I find it at negative 1.96. If you had looked up the positive z value, you would look up all this area, 0.025 plus 0.95, and then you would find the z value at positive 1.96. Okay, so it doesn't matter either one. So that's how you would find it by looking at the z table. So when I finish this page, I'll show you how to do it with Excel. Then you can decide which one you want. But either way, you need to draw the graph so you can understand what it is you're looking for. Okay, any questions for me? So I'm going to move on to the formula. So now we have p hat, which is 0.59 plus or minus z, which we found to be 1.96, and then this entire thing is 0.59 times minus 0.59 divided by 200, and the whole thing is square root. Okay, so now I would like to have Abraham, can you give us the value for this? So this is my standard error of sampling distribution. Detrick, do you have the answer for this?
I got 0.0329. I'm not sure that's right.
Okay, anyone else? Let's double check. I don't have the answer either. Anyone have this answer? So you're doing 0.59 times 1 minus 0.59 divided by 200, the whole thing square root. Okay, seems like you'll have similar answers. Okay, 0.035. Okay, let's go with that. So the next thing I want is, Conrad, can you do the margin of error? Okay, so Conrad, you're doing margin of error, which is the sampling error times 1.96.
Said the sampling error times
1.96. So basically that right side of the formula.
It's gonna be 0.0686.
Okay. Anyone else confirm with us that 0.0686, same thing. Okay, thank you. It's good to get into the habit of using 4 decimal places, because if you round it too early, your answer might be off at the end. So this is good practice to keep it like that. Okay, so now I'm going to say that our answer is 0.59 plus or minus 0.0686. So I'll leave it like this because the next slide would really show you how to convert this into percentages. So I won't do it here, but I'll show you on the next slide. Okay, any questions before I switch slides? Okay, I know that I have to show you how to do this on Excel, and I will do that in a moment. But okay, so this is the next slide, and it skipped that other step that I had, which said 0.59 plus or minus 0.0686. So this is saying that the actual proportion of students who receive some sort of financial aid is 59% plus or minus 6.9%. So I'll say it again, the true proportion of students who receive some sort of financial aid is 59% plus or minus 6.9%. Okay, so I've converted it into percentage because remember we're talking about the proportion of students. So proportion means percentage. Or you could take it to the next step without showing it as a margin of error, which is your lower limit and upper limit, and indicate that the true population proportion is between 52.3% and 65.8%. So that's adding the margin of error and subtracting the margin of error to get the lower limit and upper limit. Okay, so make sure you understand that both these steps are correct and both are final. And then you have to remember that your interpretation is also the most important thing, because it's not enough just to be able to calculate the answer. You need to interpret it correctly. So we are 95% confident that the proportion of students who receive some sort of financial aid at Queen's College is between 52% and 66%. So it's okay to round it to 52% and 66%. Any questions? So let's say Queen's College was advertising how much aid that they give, and they publish this in some flyer or email saying that more than half of our students receive some sort of financial aid. Is that accurate information for them to say that more than half of our students receive financial aid? Yes, it is accurate information, because we are 95% confident that between 52% and 66% of all students receive financial aid. So it would be incorrect to say that 75% of our students receive financial aid, because that would be wrong. but they could say more than half. What I want to show you is Excel, right? So let me actually first show you the normal distribution tables so that you know where I got this number from. So I'd look at the first page because the first page has all the negative values of z, and we were looking for this area of what was it, 0.025, right? That's what we said. So that area was 0.025. So if you look, I don't know why that happened there, but if you look in the center of the table, you can find it here, 0.025. It's at this z value, negative 1.96. So that's where we got z equals negative 1.96. And automatically I would have got z equals positive 1.96 from my second page if I looked up the positive z value. Any questions about the z table, reading the z value from here? Okay, I'm going to share my Excel screen. Okay, you should be able to see it. So this is the formula you would use. I'm going to copy this and paste it into the chat box so that you can also do this on your own. But that's why I said that it's important to draw your graph. Then you know what the probability is because you have to put in that probability value. So it's actually norm.s.inv, open parentheses, and then instead of writing the word probability, we said that the negative z value that we want has that area from negative infinity up to negative z as 0.025. So make sure you type this into the Excel cell. So instead of the word probability, 0.025. Making this a little bigger, and then I hit enter, and then automatically tells me that the value for z is negative 1.96. So again, you can see here that this is the formula I used. So you can use either way, reading the table or looking it up on Excel. Question?
Yes, Professor. Just real quick, I just want to ask, when do we use norm.s.diff again? I forgot that part.
Say it again. What's your question?
So there's two formulas in Excel. It's norm.s.inv, and there's another formula that says norm.s.disk
Oh,
distribution.
right. So that is if you're using, I think the other way around, right? That's when you have the z value and you want to find the probability. So when you're flipping it. So in this case,
Oh, okay. So this one,
we
you know
would,
the percentage already. So
no, right, correct. Yeah. So this one, we know the probability. We want to get the z value. So it's the
okay, got it.
inverse.
Thank you.
And the distribution is the other way around. Okay, so
Okay.
these formulae are in the slides of chapter 11. So, have it in front of you when you're doing the exercises if you decide to use Excel. So you can see it's pretty simple, but if you put in the wrong probability, for example, so let's say you couldn't figure out that the area from negative infinity up to z was 0.025 and you put in 0.95, that's wrong. That's not the z value. So you need to be able to be aware and visually understand what it is. Okay, questions? Okay. So now going back to my slides. Okay, so I'm going to go to the next slide, which is this. And it's a poll, but let's start with the first question. And then I'll put up the poll. So question number 1 says, there is a 95% probability that the proportion lies between 52% and 66%. So just answer that question for now, and I'm setting up the poll here. And on the top, I'm going to write the answer that we had, that we calculated, because you don't have that in front of you. Okay, 30 seconds. Okay, I'm stopping it here. So you can see here, most of you said the answer is true. And I'm going to say that the answer is false. So for those of you who said the answer is false, can you explain?
Hi, yes, I would say because it's 95% confidence. What? And not probability in this case.
Minus.
Okay, so I think Jeffrey agrees with you on that. Not probability. So reading the question says that there is a 95% probability that the proportion lies between 52% and 66%. Rad, you say the same thing. The question is stating that, or implying that the proportion that you found out is variable. It's implying that it happens sometimes. It's implying that it's not fixed, that it keeps moving. Well, that's wrong, because what you calculated, it's fixed. It might be unknown, it might be an estimate, but it is fixed, and you are 95% confident of your answer. So it's not that it's a 95% chance of something happening or probability of it happening. So that's why this statement is false. So be very careful when you're reading the different interpretations, because you have some homework exercises like this and you will be marked wrong. Okay, so let's do the next one. When the interval is wider, it will more likely include the population. So let me post this. Okay, 30 seconds. Okay, stopping here. So this answer is true. You can see here when the interval is wider. Okay, so first we were dealing with a 95% confidence interval, and these are our answers, 52%, 66%. Now we're saying when the interval is wider. So wider could be, and I'm making up some values here. Let's say it's between 45% and 70%. I made up those values. So now my interval is wider. That means it could be 99% confidence, right? Because now I have a lower limit and a higher upper limit. So my interval is wider, meaning more area in the center, maybe 99% confidence. So now it's saying that it will more likely include the true population proportion. So that's correct. Because I have a wider interval, it's more likely, and I'm 99% confident. So the answer is true. Rad, you said that you thought it was talking about the shape of the curve being wide. So yes, not the shape. So I'm talking about the area in the center, the actual interval. So for that reason, this answer is true. Now we understand that a wider interval will more likely include the population proportion P, but it doesn't really give me enough information. It's not precise. I mean, is it really helpful to know that anywhere between 45% to 70% of students receive financial aid? It's not a really precise number. I would like it to be more precise. The closer the interval is, or the narrower the interval is, it might not have a very high confidence with the answer, but at least it's more precise. So we need to understand that these are different ways of presenting your answer. Let's look at question number 3, looking at the PS value in this example. So in this example, sample proportion was 59%. If that value is reduced, the confidence interval always narrows. So again, here's your poll. And you can answer. Okay, stopping it here. So this shows that you're about even, and this answer is true. So looking at the sample proportion in this, if you think about the formula, sample proportion, so that would be this value, it's included in this calculation and it's included in this calculation, the margin of error. So if you make that value smaller, and you can do this on your own, you'll see that the confidence level, the interval, actually narrows. The actual interval always gets smaller. Okay, then when you have a smaller sample proportion value. Number 4, 59% receive financial aid with sampling error plus or minus 6.8%. So is that true or false? So this is question number 4. So I'll read it again. 59% receive financial aid with sampling error plus or minus 6.8%. Okay, 20 seconds. So this answer is true. Does anyone want to explain why? So for the ones who said yes, why do you think it's true? So this is a different way of answering and interpreting your calculations using margin of error or sampling error. It's the same thing, right? Sampling error is the same thing as margin of error. Yes, just answered your question, Red. So that means you're interpreting it based on this, which is 59% receive some sort of financial aid, plus or minus a sampling error of 6.8%. So again, get familiar with the different terms. It means the same thing. Questions for me? Okay, the last thing I'm going to do is show you where this is applied in the real world. And Urmila, to answer your question, standard error of sampling is not sampling error. Correct. So there is a difference. Standard error of sampling is that, I can do it right here, PS 1 minus PS, just the inside of that square root. Just this would be the standard error of sampling. The sampling error is this portion of the confidence interval formula because it includes the critical value z. So when you take z times all this, then it's the sampling error, or then it's the margin of error. Okay, so there is a difference. What I just put up here, this link, I'm going to share with you now because I want to show you that confidence intervals are actually used in the real world. I'm not making this stuff up. So let me show you sharing this. So you should be able to see this now. This is from the National Weather Service Forecast Office, and I put in New York City Central Park. So you can see here that you're looking at a graph. It's a 3-month temperature outlook. On the x-axis, it's the average for October, November, December, January, and so on. So 3-month period. On the y-axis, it's the average 3-month temperature. So for example, let's look at October, November, December. This is a 99% confidence interval. The lower limit is, so what I should expect, remember this is an estimate, right? I should expect October, November, December to have a lower limit temperature of, let's say, about 42 degrees Fahrenheit and an upper limit of 52 degrees Fahrenheit. And this would be my point estimate, the center of that confidence interval. And it's 99% confidence. If I want to be, let's say, 90% confident of my answer, now you can see the intervals have kind of got narrower. So the lower limit is 45 degrees Fahrenheit to about 51 degrees Fahrenheit. Okay, so this helps us predict temperatures. And I think if you can click on different things, it gives you the actual value. So I don't want to mess this up and lose this. There's tabular data, but it gives you the lower limit, upper limit for the individual 3-month period. Okay. So that's all for today. I'm going to stop recording.